Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine opening like a photo album of the universe when it was just a toddler.
Oh, that's a great way to picture it.
Right. Like you would intuitively expect to see just complete chaos.
Absolutely.
Just random, messy infant galaxies scattered completely haphazardly in the void, like oblivious to one another, just trying to ignite their first stars.
Yeah, just doing their own thing in isolation.
Exactly. But recently, astronomers developed the optical precision to actually look back 12.6 billion years into that exact epoch.
And they definitely didn't find chaos.
No, they didn't. They found these sprawling, highly structured, interconnected metropolises.
Incredible.
And these structures were already dictating exactly how fast those infant galaxies would grow, how they would physically shape themselves, and ultimately how they would die.
Yeah.
We're essentially looking at the exact moment the cosmos began playing the nurture card, but on a galactic scale.
Right. And that's huge, because the prevailing assumption in cosmology for a very long time was that in the early universe specifically, that era around 1.2 billion years after the Big Bang galaxies evolved almost entirely through secular processes.
Which means what? Just internal stuff.
Exactly. Meaning their growth was driven by their own internal mass, their own gas reservoirs, and just their isolated gravitational dynamics.
So totally the nature side of the equation.
Right. You're born with a certain amount of gas, and you just build stars until you run out.
Got it.
So finding these highly evolved, dense environments acting as architectural constraints so early on, it completely upends our timeline of how structures form.
Because we've always known that in our current era, the mature universe galaxies are absolutely dominated by their environments.
Oh, without a doubt.
You look at massive structures like the Coma Cluster, which has thousands of galaxies, and it's obvious that gravity has corralled them together into these huge metropolises of light and hot gas.
Right. But the assumption was always that this clustering and, the environmental effects that come with it took billions of years to mature.
We assumed it took time for the cosmic web to tighten its grip.
Exactly. And that timeline constraint was largely based on the sheer scale of the distances involved.
And cosmic expansion, right?
Yeah, the mechanics of expansion. The expansion of space acts as this persistent counterforce to gravitational collapse.
It's like a tug of war.
That is the perfect analogy. To form a massive galaxy cluster, gravity has to win a tug of war against the Hubble flow.
The underlying expansion of space itself.
Right. And on the absolute largest scales, the expansion always wins. Space is pulling apart faster than gravity can pull it together.
But on localized scales.
On localized scales, if a region has a high enough initial density, its gravitational self-attraction can actually halt that local expansion.
It fights back and wins.
Yeah, and it causes the whole region to collapse inward. We actually call this critical threshold the turnaround radius.
Okay, so to understand how these environments shaped early galaxies, we need to look at the seeds of these modern massive clusters.
The protoclusters.
Right, the protoclusters. And if a protocluster is essentially a localized region that successfully overcame the Hubble flow, it must have started with a pretty significant advantage.
Oh, absolutely. It had to be an overdensity that was baked into the universe from the very beginning.
Just like a heavier pocket of space?
Basically, yeah. Those primordial overdensities are the crucial starting point, because right after the Big Bang, matter was distributed with almost perfect uniformity.
Almost perfect.
Almost. But there are these quantum fluctuations in that incredibly dense early state. And during cosmic inflation, those microscopic variations were stretched out to macroscopic scales.
Leaving behind these slight variations in density.
Right. And over the first few 100 million years, dark matter, which doesn't interact with light, so it can collapse much earlier than regular gas, began to pool into these slightly denser regions.
Forming the invisible scaffolding of the universe.
Exactly. The dark matter halos.
Wow.
And these dark matter halos serve as the deep gravitational wells that anchor literally everything else. As they grew, their gravity pulled in the primordial hydrogen and helium gas.
And that gas compresses, cools, and ignites to form the first stars.
And infant galaxies, yes. So a protocluster is really just a vast, sprawling network of these early dark matter halos connected by filaments of gas.
Just slowly drawing together toward this inevitable massive gravitational collapse.
Right. And within those dense collapsing regions, we see the onset of this environmental effect.
Because in modern galaxy clusters, we know that environment is incredibly hostile.
Yeah, it's brutal.
Like if a galaxy falls into a modern cluster, it doesn't just join the group peacefully, right?
Uh-huh.
It gets fundamentally altered.
Yeah, it's violently changed. We see these isolated field galaxies as beautiful, gas-rich, star-forming spirals.
Like our Milky Way.
Exactly like the Milky Way. But the galaxy's trapped inside massive clusters. They're often massive ellipticals, entirely devoid of cold gas.
Completely incapable of forming new stars.
Right. Astronomers call it the classic red and dead classification.
Which sounds so bleak. But what actually causes a galaxy to become red and dead when it falls into a modern cluster?
Well, the mechanics driving it are thermodynamically really complex because space within a cluster is not a vacuum.
It's not empty.
Not at all. The immense gravitational pull of the entire cluster accelerates all this infalling gas to tremendous velocities.
And as it collides.
As it collides, it shock heats to millions of degrees. It forms what we call the intracluster medium, or the ICM.
So it's a plasma.
A superheated plasma. It's actually so hot it emits primarily in X-rays.
Okay, so when a beautiful gas-rich spiral galaxy plunges into this modern cluster, it's not flying through empty space.
No.
It's literally slamming into a wall of superheated plasma at thousands of kilometers per second.
Yeah, and the fluid dynamics of that collision are just devastating for the galaxy.
I can imagine.
It experiences extreme ram pressure. The static pressure of the hot ICM basically acts like a hurricane-force headwind.
Well.
And it physically strips the cold star-forming gas right out of the galactic disk.
Just blows it away.
Yeah, trailing it behind the galaxy like the tail of a comet. And without that cold gas reservoir, star formation ceases almost immediately.
It's just shut off.
Completely.
Yeah.
And furthermore, the galaxy undergoes this process we call strangulation or starvation.
Oh, which also sounds terrible.
It is. The extended halo of hot gas that would normally cool down and feed future star formation is also stripped away.
So it loses its current gas and its future supply.
Exactly. The galaxy is left with only its existing stars, which just slowly age, turn red, and eventually die out.
But see, that brings up a massive physical contradiction when we talk about the early universe.
It really does.
Because if this environmental effect relies on this incredibly dense superheated plasma to act as a hurricane wind, how could that effect possibly exist only 1.2 billion years after the Big Bang?
Right.
I mean, a protocluster by definition hasn't fully collapsed yet, right?
Exactly. The dark matter halos are still merging.
The gas hasn't had billions of years to shock heat to those extreme X-ray temperatures.
You've highlighted the exact theoretical tension that made this specific era so critical to observe.
Because the plasma shouldn't be there yet.
Right. The classical mechanisms we just talked about, the ram pressure stripping, the shock heating, they require a mature, settled cluster.
A finished product.
Yeah. A protocluster at that early epoch, what we call redshift 4 or 5, is basically a sprawling, unfinished construction site.
The gas is just streaming in along filaments.
It isn't a static, superheated bath yet. So if we observe environmental effects altering the physical structure of galaxies in a protocluster,
Which we did.
it implies that the mechanisms of cosmic nurture operate through entirely different physics in the early universe compared to today.
Probably more accretion-driven, right? Like feeding instead of stripping.
Exactly. It forces us to ask whether the early environment acts as a weapon that strips a galaxy or as a hyper-efficient feeding tube that alters how it grows.
But investigating that requires observational data that is, frankly, notoriously difficult to capture.
Extremely difficult.
Because we aren't just looking for one faint object. We are looking for a sprawling, diffuse web of faint objects spread across a massive volume of space.
Seen as they were 12.6 billion years ago.
Yeah. You can't just point a standard telescope at a blank patch of sky and hope to recognize a protocluster.
No, the observation challenge is huge. It's twofold, really. First, the intrinsic faintness of objects at that distance means you need an enormous light-collecting area.
A massive mirror.
A massive primary mirror. And second, protoclusters are not compact.
Because the universe expanded.
Right. The universe has expanded so much since that light was emitted. A single protocluster from that epoch spans an enormous angular size on the night sky today.
So if you use a telescope with high magnification but a tiny field of view,
you might see one or two galaxies, but you completely miss the forest for the trees. You'd never recognize the underlying macrostructure.
Which is exactly why astronomers needed an instrument like the Subaru telescope in Hawaii.
Yes.
Specifically, utilizing its Hyper-Supreme Cam, or HSC.
That camera is incredible.
It's an engineering marvel. It's designed specifically for wide-field surveys. It lets researchers map vast swaths of the deep universe simultaneously.
But even with a massive field of view, looking at visible light from that era is completely useless.
Right, because of redshift. The ultraviolet and visible light emitted by those early stars has been physically stretched by the expansion of space over 12.6 billion years.
Yeah, the cosmological redshift is the defining hurdle of high redshift astronomy. Space itself is expanding, and as a photon traverses that expanding space, its wavelength is physically stretched out.
So a photon emitted in the ultraviolet by a hot young star in the early universe
will arrive at Earth billions of years later with its wavelength stretched all the way into the red or infrared part of the spectrum.
Right, so if we want to trace the skeletal structure of a protocluster, we can't look for just the broad spectrum of starlight.
It's too faint and smeared out.
Exactly. We need a specific, highly concentrated signal that survives that cosmic stretching. We need a tracer.
And in cosmology, the ultimate tracer for early star formation is the Lyman alpha emission line.
Let's break that down, because the physics underlying Lyman alpha emission is just so cool. It relies on the fundamental quantum mechanics of the hydrogen atom, right?
Yes, and hydrogen, being the primordial building block of the cosmos, was overwhelmingly abundant back then.
It was everywhere.
Exactly. So when a young, massive galaxy undergoes a starburst phase, it synthesizes populations of incredibly hot, massive stars, the O and B type stars.
And to be clear for everyone, these aren't stars like our sun.
Oh, not at all.
These are stellar behemoths. They burn at furious temperatures, and they exhaust their nuclear fuel in a matter of millions of years rather than billions.
Yeah, they live fast and die young. And because they burn so hot, the peak of their radiation sits deep in the extreme ultraviolet.
They're essentially cosmic floodlights.
That is exactly what they are, blasting high-energy ionizing radiation into the surrounding gas.
And that surrounding gas is thick with neutral hydrogen.
Right. So when a high-energy, extreme ultraviolet photon from one of these massive stars collides with the neutral hydrogen atom,
it transfers its energy to the atom's single electron.
Yes. And in the quantum mechanical model of the atom, electrons occupy specific quantized energy levels.
They can't just be anywhere.
No, they have defined orbits. So the incoming photon provides enough energy to excite the electron from its ground state, the lowest energy level, n equals 1, up to a higher energy orbital.
But quantum systems inherently seek their lowest possible energy state, right?
Yeah.
The universe absolutely abhors an excited electron.
It really does. It can't maintain that precarious higher orbit.
So it drops back down almost instantaneously.
Right. But energy must be conserved. When the electron transitions from that first excited state, n equals 2, back down to the ground state, it has to release the exact quantum of energy it originally absorbed.
And that energy is released as a single photon.
Exactly. And because the energy difference between those two specific orbitals in a hydrogen atom is an absolute, unchanging physical constant.
The emitted photon always has the exact same wavelength.
121.6 nanometers.
Deep in the ultraviolet.
Yes.
So you have millions of these massive stars acting as engines, pumping extreme UV radiation into the surrounding hydrogen clouds.
And the hydrogen clouds respond by fluorescently glowing at this one highly specific wavelength.
It basically turns the entire galaxy into a blazing cosmic neon sign.
It's exactly how it acts, flashing open for business, making stars.
I love that. In an epoch that is otherwise incredibly difficult to observe, these galaxies are broadcasting this brilliant, unmistakable signal tied directly to the furious birth of new stars.
And galaxies identified by this specific signature are appropriately called Lyman alpha emitters. Because this emission line is intrinsically so bright, it acts as a beacon.
It lets us pinpoint intense star formation across immense distances.
Right. However, actually capturing that 121.6 nanometer photon from Earth requires incredibly precise interference filters.
Because of the redshift we discussed earlier, The photon leaves the galaxy at 121.6 nanometers. But as it travels for 12.6 billion years through expanding space, that wavelength stretches.
Yeah, but the beauty of it is we can calculate the exact redshift for the specific epoch we want to observe.
Because math works.
Math works. The era of 12.6 billion years ago corresponds roughly to a redshift of z equals 4.5 to 5.
Okay.
And we know mathematically exactly how much a 121.6 nanometer wavelength will be stretched by a redshift of that magnitude.
It pushes the wavelength entirely out of the ultraviolet, right?
Yes. Through the visible blue and green, and lands it squarely in the longer red wavelengths of the optical spectrum.
So astronomers design a custom piece of glass, a narrow-band filter, that physically blocks out the entire electromagnetic spectrum except for that one mathematically predicted stretched-out wavelength.
It's a bespoke filter.
And they place this in front of the hypersuprime cam, and they just stare at a massive patch of the sky.
Right. They aren't looking at stars in our galaxy or even normal galaxies in the background.
They are basically wearing specialized thermal goggles.
That's a great analogy. Goggles that only let them see the specific glow of Lyman alpha emitters from exactly 12.6 billion years ago.
It's a technique of extraordinary precision.
It really is. By utilizing these narrowband filters on wide-field imagers, you essentially take a highly specific slice of the universe at one exact moment in cosmic time.
You're just mapping the distribution of these glowing beacons.
Yeah. And if the universe were truly unorganized at that stage, you would expect to see a relatively uniform, random scattering of Lyman alpha emitters across the field of view.
Just dots randomly everywhere.
Right.
But that is the exact opposite of what the Subaru data revealed.
Totally the opposite.
When they mapped this specific epoch, they found an astonishing concentration of these emitters. They located a massive, highly structured protocluster.
And they named it the Loktak Protocluster.
Which is such an amazing discovery.
The identification of the Loktak Protocluster is a landmark observation, mainly because of its profound morphological complexity.
Right, because the researchers didn't just find a singular dense knot of galaxies. The mapping revealed this expansive, multi-component architecture.
It was highly structured.
And the name itself provides a perfect geological metaphor for the structure. It's named after Loktak Lake in northeastern India.
Right, in Manipur.
Yeah. And that lake is famous for its phumdis.
The floating islands.
Exactly. These massive circular floating islands of organic matter and vegetation. Some of them are large enough to support entire localized ecosystems, like people live on them.
Wow.
But they are all floating within and inextricably linked to this one singular aquatic system of the lake.
And the mapping of the protocluster mirrors that topology perfectly.
It really does. The narrowband data revealed 4 distinct, intensely dense subclusters.
4 separate nodes of hyperactive star formation.
And these nodes are physically separated by vast distances across the early cosmic web, yet the kinematic data and the spatial distribution confirm they are absolutely gravitationally bound.
They are 4 massive islands floating within a shared, unseen ocean of dark matter.
It totally validates the bottom-up model of hierarchical structure formation on a grand scale. We are looking at the fundamental building blocks of a future supercluster before they have consolidated.
Right. Ronaldo Leistrom, the lead author of this study from the National Astronomical Observatory of Japan, accurately described these nodes as the construction sites of the most massive structures in the present-day universe.
Construction sites. It's so appropriate because it highlights the dynamic, unfinished nature of the whole system.
Very unfinished. In the billions of years following this 12.6 billion-year-old snapshot, the profound mass of that shared dark matter halo would act as a massive gravitational funnel.
So those 4 separate islands,
They're locked in an inexorable inward spiral.
destined to crash.
Through the process of dynamical friction, where massive objects lose orbital energy as they move through a background of smaller particles and dark matter, their orbits will decay.
Look, just slow down and fall in.
Exactly. They will eventually fall toward the very center of the system.
And the eventual collisions between those 4 nodes would be unfathomably violent.
Truly cataclysmic.
As those individual subclusters merge, the dark matter halos intertwine, but the baryonic matter, the gas and the galaxies, slams together.
Yeah, and those mergers would trigger massive shock waves through the newly forming intracluster medium.
Which would incite even more starbursts before eventually heating the gas to the point where star formation is permanently quenched.
Exactly what we discussed earlier.
Yeah.
The Loktak Protocluster is definitively destined to become one of the monolithic, spherical, X-ray emitting superclusters we see in the local universe today.
So finding this structure provided the perfect laboratory. It proved that complex multi-node environments existed extremely early in cosmic history.
But just establishing the presence of the environment is only the prerequisite, right?
Right. The main question was, is this environment actually doing anything?
Yes. The primary scientific objective was to determine if this sprawling, interconnected environment was actively altering the evolutionary pathways of the individual galaxies residing within it.
Like, did living in one of these 4 dense islands actually change a galaxy's physical structure compared to a galaxy just growing up in complete isolation?
And to answer that, the wide-field survey capabilities of the Subaru telescope were no longer sufficient.
Because Subaru is designed to find the city.
Right. To understand the architecture of the individual buildings within the city, you need unprecedented spatial resolution.
You have to zoom in.
You have to transition from wide-field mapping to deep, targeted observations.
Which necessitates space-based observatories.
Exactly. The research team employed a multi-wavelength approach, combining the high-resolution visible light capabilities of the Hubble Space Telescope with the revolutionary infrared sensitivity of the James Webb Space Telescope.
GWST doing what it does best. And the methodology here relies on using different wavelengths of light to isolate different physical components of the galaxies, right?
Yeah. They performed a massive comparative analysis. They analyzed the galaxies deeply embedded inside the dense nodes of the Loktak Protocluster.
City dwellers.
Right. And they compared them directly to field galaxies. Galaxies from the exact same redshift, the exact same 12.6 billion-year-old epoch, but located in low-density, isolated regions of the cosmic web.
Rural galaxies.
Exactly. It is the ultimate controlled experiment for the nature versus nurture debate in astrophysics.
Because by isolating the epoch, you completely remove time as a variable. They're the exact same age.
Right. The only major variable altering their evolutionary state should be the local density of their environment.
So they scrutinized the physical morphology of these 2 groups of galaxies across 2 distinct spectral regimes, right? The rest frame ultraviolet and the rest frame optical.
Yes. Let's break down the physical significance of those 2 spectral regimes.
Let's do it.
The rest frame ultraviolet light, which we observe today, redshifted into the visible or near infrared, acts as a direct tracer for active, ongoing star formation.
As we established with the Lyman alpha mechanics, UV radiation is dominated by the most massive, hottest stars.
Right, the O and B types.
And because those stars have lifetimes of only a few million years, any UV light we detect must be coming from stars that were born almost exactly the moment the light was emitted.
Exactly. Ultraviolet emission provides an instantaneous pulse check of the galaxy. It delineates the exact regions where giant molecular clouds are actively collapsing to form new stellar populations right now.
Okay, so when the researchers analyzed the spatial extent of the ultraviolet emission, basically measuring the physical size of the star-forming cores, what did they find?
They found a remarkable parity.
They were the same.
Statistically indistinguishable. Whether a galaxy was deeply embedded in the chaotic, dense environment of the Loktak Protocluster or floating completely alone in the cosmic voids.
The active nurseries looked identical.
Yes. The physical size of their central star-forming engines was the same. The environment did not appear to be altering the spatial distribution of current star formation in the core.
So if the investigation had just concluded there, if they only had the ultraviolet data, you might actually conclude that the early environment had no structural impact at all.
You would. You might erroneously conclude that nature entirely dominated nurture in the early universe.
But the rest frame optical data.
Yes. Captured meticulously by JWST's near-infrared camera, it revealed a drastically different reality.
Because the optical light, which has been redshifted deep into the infrared where JWST excels, doesn't trace the massive, short-lived hot stars.
No, it traces the older, cooler, lower-mass stars, the K and M type dwarfs and giants.
The stars that live for billions of years.
Right. Therefore, they represent the accumulated history of the galaxy. The rest frame optical emission maps the stellar mass distribution that has already been assembled over the galaxy's entire lifetime up to that point.
It provides the structural footprint of the established galaxy, independent of wherever the current transient bursts of new star formation happen to be occurring.
Exactly.
So I like to think about it like looking at modern cities. The UV light shows us the bustling downtown district where all the new frantic construction is happening right now.
That's a perfect way to visualize it.
But the optical light shows us the sprawling suburbs, the historical footprint of the city's growth over time.
Yes.
And when they compared the optical footprints, the suburbs of the cluster galaxies to the isolated field galaxies,
The parity vanished entirely.
the divergence was profound.
The data explicitly demonstrated that the galaxies residing within the dense nodes of the Loktak Protocluster were, on average, 1.4 times larger in their rest frame optical emission than their isolated counterparts.
A 40% increase in physical size. That is a massive structural discrepancy.
It really is.
So the central downtowns are exactly the same size, but the established suburbs of the cluster galaxies have sprawled outward immensely.
Proving definitively that the environment is actively manipulating the physical architecture of the galaxies.
But it's doing so primarily on the outskirts.
Right, leaving the central star-forming cores relatively untouched.
This morphological disparity is really the crux of the discovery, isn't it?
Absolutely, because it indicates that the mechanisms of environmental influence in the early universe are fundamentally different from the gas-stripping processes that dominate modern clusters.
Right, because in a mature cluster, the environment strips the gas and shuts down star formation in the core.
But in this early protocluster, the environment is rapidly building up the extended stellar envelope while the core just continues to function normally.
Okay, so that requires us to analyze the actual mechanics of mass assembly in a dense environment. Like, if the central engine isn't working any harder than an isolated galaxy, how is the cluster galaxy building these massive outer suburbs so rapidly?
It implies the mass isn't being generated internally.
It's being accreted externally.
Yes. And the theoretical frameworks for galaxy formation strongly support that conclusion. In a high-density node like the Loktak Protocluster, a massive central galaxy sits at the nexus of intersecting dark matter filaments.
These filaments act as cosmic highways.
Exactly. They channel continuous streams of cold primordial gas directly into the gravitational well of the galaxy.
This phenomenon is known as cold stream accretion, right?
Yes. It provides a massive influx of raw material to the outer regions of the galaxy.
So it's essentially being force-fed by the cosmic web.
Yes, but it's not just pristine gas flowing in. The dense environment of a protocluster is crowded with smaller satellite dwarf galaxies.
Right, so the frequency of minor mergers in a protocluster environment must be exponentially higher than in isolated regions.
Oh, incredibly high. The deep gravitational well of the primary galaxy constantly captures these smaller satellite galaxies.
And as a dwarf galaxy orbits the larger host.
Gravitational tidal forces begin to shred it. The stars and gas from the dwarf galaxy are literally stripped away and deposited into the extended halo of the primary galaxy.
It's a process of violent gravitational cannibalism.
It really is.
Yeah.
The primary galaxy isn't necessarily forming all those older stars in its massive new suburbs. It's stealing them from its neighbors.
Just ripping them apart.
Yeah. Over millions of years, as it shreds and consumes multiple satellite galaxies, those accreted stars build up the extended, diffuse optical footprint that JWST detected.
So it's this combination of cold stream accretion along dark matter filaments and the elevated rate of minor mergers.
Exactly. It perfectly explains the physical characteristics observed in the Loktak Protocluster.
The environment acts as an accelerant for mass assembly.
The galaxies in the dense nodes have preferential access to the cosmological buffet, basically.
Allowing them to rapidly assemble extensive stellar envelopes far earlier than galaxies starved of those resources in the isolated voids.
Right. The ultimate verdict on the nature versus nurture debate in the early cosmos is unambiguous at this point.
Nurture plays a massive structural role almost from the very beginning.
Absolutely. Just 1.2 billion years after the Big Bang, which is barely 9% into the universe's current lifespan, a galaxy's physical evolution was already deeply dependent on its cosmological zip code.
You cannot model the early universe assuming galaxies evolved as isolated islands. They were heavily manipulated by the interconnected ecosystem they inhabited.
And it forces a necessary paradigm shift in our cosmological simulations. Theoretical models must prioritize the macro-environmental context even at extreme redshifts.
The gravitational web, the hydrodynamics of the inflowing gas, the proximity and kinematics of neighboring dark matter halos.
Right. These are not secondary effects that emerge billions of years later. They are the primary drivers of morphological evolution from day one.
But, this accelerated growth model presents a really fascinating dichotomy to me.
How so?
Well, if the early protocluster environment is basically a hyper-efficient feeding mechanism that builds these massive galaxies rapidly, how do we reconcile that with the eventual fate of these structures?
Right.
Because we established earlier that in the modern, mature universe, cluster galaxies are red and dead. The environment eventually chokes them. So, does the very process of this rapid environment-driven mass assembly inadvertently seal their fate? Like, does the gluttonous growth trigger the mechanisms of their own destruction?
It does. The thermodynamics of the environment virtually guarantee it.
It's a double-edged sword.
Exactly. In the early epoch, the dominant process is the accretion of cold gas along the filaments, which fuels the growth. However, as the protocluster continues to pull in more mass, the depth of the gravitational potential well increases significantly.
And so the velocities of the infalling galaxies and gas clouds increase.
And as those velocities increase, the collisions become far more energetic.
The friction intensifies.
Precisely. The kinetic energy of all that infalling matter is converted into thermal energy through massive shocks.
So the diffuse gas permeating the protocluster begins to heat up rapidly.
Yes. Eventually, the temperature of this intercluster medium crosses a critical threshold. It becomes so hot that it can no longer condense and cool down to form molecular clouds.
So the cold streams that were feeding the galaxies are disrupted.
Evaporated by the expanding volume of superheated plasma.
The buffet just closes.
Exactly. The environment transitions from a feeding tube to a blast furnace.
And as that plasma thickens and heats up, the ram pressure stripping we talked about earlier finally kicks in.
Yeah. The galaxies, which grew so massive and bloated during the early feeding phase, now find themselves flying through a dense, hot wind that violently tears away whatever cold gas they have left.
It is such a profound evolutionary trajectory. And furthermore, the rapid mass assembly in the early universe often fuels the rapid growth of the galaxy's central supermassive black hole, right?
Yes, that's another crucial factor. As massive amounts of gas funnel into the galactic center, the black hole begins to accrete matter at a phenomenal rate, becoming an active galactic nucleus, or AGN.
And AGN feedback is perhaps one of the most violent regulatory mechanisms in the universe.
Oh, without a doubt.
We actually see this actively happening in other structures from this era, like the so-called spiderweb protoclusters.
The spiderweb protoclusters are exquisite examples of environment-driven regulation.
So what exactly happens there?
In these systems, the central supermassive black hole is accreting matter so voraciously that it generates colossal jets of relativistic particles and intense radiation.
And these jets punch out into the surrounding intracluster medium.
Right. The energy injected by the AGN is so immense that it physically blows the cold gas out of the central galaxy and heats the surrounding environment, effectively halting star formation not just within the host galaxy, but across massive swaths of the entire cluster.
Wow. So the central black hole essentially acts as a thermostat for the entire galactic neighborhood.
Exactly. If the environment feeds the galaxy too quickly, the black hole ignites and violently shuts off the fuel supply for everyone.
It's a self-regulating macro system.
Yeah.
And we also see this extreme feedback in the distant hot dust obscure galaxies, or hot dogs, right? The ones discovered by JWST.
Yes, the hot dogs represent an extreme phase of this evolutionary cycle.
They are just incredibly massive, hyperluminous galaxies in the early universe that are completely enshrouded in thick, obscuring clouds of dust.
And the infrared radiation they emit is staggering. Recent kinematic analysis using JWST suggests that much of this dust is not settled in the galactic disk, but is being violently expelled outward along the polar axis of the galaxy.
Driven by the intense radiation pressure of a buried, hyperactive, supermassive black hole.
Exactly. The central engine is literally blowing the galaxy's raw building materials out into intergalactic space.
And that expelled dust and heavy element-enriched gas eventually cools and mixes into the surrounding environment, chemically altering the intracluster medium for the next generation galaxies.
The feedback loops are just endless and deeply intertwined.
Nothing in the universe evolves in pure isolation. The early cosmos was a chaotic, violent, but fundamentally interconnected thermodynamic ecosystem.
And the discovery of the morphological differences in the Loktak Protocluster provides the foundational evidence for that interconnected reality.
However, as robust as the multi-wavelength data from Subaru, Hubble, and JWST is, the Loktak Protocluster remains a single, albeit massive, data point.
Right, it's just one structure. To elevate this from a profound observation of one specific region to an ironclad universal law of early galaxy formation, the sample size must increase dramatically.
We need to know if the Loktak Protocluster was a unique anomaly, like a particularly weird, hyperactive neighborhood, or if this rapid, environment-driven structural inflation is the standard rule for all dense environments in the early universe.
And that requires mapping and analyzing dozens, if not hundreds, of these ancient structures.
Which brings us to the next generation of astronomical instrumentation, which is being brought online specifically to execute that massive survey.
Yes. The Subaru telescope itself is currently undergoing a transformative upgrade to its spectroscopic capabilities.
A prime focus spectrograph, right, the Hula PFS.
Exactly. It will revolutionize our ability to map these early structures. Because while the Hypersa Prime Cam can image vast areas and identify candidates using narrowband filters, the PFS will allow astronomers to simultaneously capture the detailed spectra of thousands of individual objects across a massive field of view.
And spectroscopy is the key to unlocking the kinematics.
It absolutely is.
Instead of just seeing a glowing dot and estimating its redshift based on a filter, spectroscopy breaks the light down into its constituent wavelengths, revealing the exact chemical signatures and the precise velocity of the galaxy.
So you can measure exactly how fast those 4 massive nodes in the Loktak Protocluster are moving toward each other.
It transitions the data from a two-dimensional map into a fully realized three-dimensional kinematic model.
Exactly. Furthermore, the development of the next-generation wide-field adaptive optics system, known as ULTIMATE, will dramatically reduce the blurring effects of Earth's atmosphere over unprecedentedly large fields of view.
So this will allow ground-based observatories to achieve spatial resolutions that rival space telescopes, but across much larger areas of the sky.
Right. And the synergy between those massive high-resolution ground surveys and the continued targeted infrared supremacy of the James Webb Space Telescope is going to define the next decade of observational cosmology.
They will systematically hunt down these ancient construction sites, peer through the dust, and map the optical footprints of the galaxies inside them.
And I would heavily bet that the Loktak mechanics, the rapid environment-driven assembly of galactic suburbs, will prove to be the universal standard.
The principles of thermodynamics and gravity strongly suggest you are correct. I mean, the underlying physics of cold stream accretion and dynamical friction are not localized phenomena.
No, they are universal mechanics dictated by the distribution of dark matter.
From the microscopic quantum fluctuations in the first fractions of a second to the sprawling multi-million light-year filaments of the cosmic web, the architecture of the space adding a galaxy inhabits fundamentally and unavoidably dictates the structural object it will become.
It really is a staggering realization about the mechanics of the cosmos.
The universe didn't wait billions of years to mature before enforcing the rules of structure and environment.
Not at all.
Just 1.2 billion years in, the invisible scaffolding of dark matter was already acting as an inescapable evolutionary force. If a galaxy was born in the dense hub of a protocluster, it was already rapidly pulling in mass, tearing apart its smaller neighbors, and sprawling outward into a massive structural footprint, operating under a completely different set of physical rules than a galaxy born in the isolated voids.
The environmental effect was inextricably woven into the fabric of galaxy evolution from the earliest conceivable stages of structure formation.
And there's a profound philosophical resonance in that scientific reality.
There is.
Think about it. We constantly analyze how we are shaped by our own environments, how our cities, our communities, the resources available in our neighborhoods, and the local structures we inhabit dictate our growth and our trajectories.
And it turns out the most incomprehensibly massive structures in the cosmos are subject to the exact same fundamental rule of nature.
At every scale of existence, from the microscopic behavior of excited electrons, to the psychological development of humans, to the thermodynamic evolution of entire galaxies, we are all products of the environments that surround us.
The universe itself is a product of its environment.
It perfectly bridges the gap between the esoteric physics of early structure formation and our intuitive understanding of interconnected systems. We are essentially observing the macro-scale equivalent of a universal truth.
It's beautiful, honestly.
It is. I want to leave you, the listener, with a final thought to mull over long after this discussion ends. We have spent this time detailing how astrophysicists utilize the specific quantum mechanics of Lyman alpha emission, massive wide-field surveys, and precision infrared mirrors to look back 12.6 billion years.
Right.
They finally developed the exact right filter to see the invisible scaffolding that was shaping the Loktak Protocluster. They found the neighborhood that was manipulating the galaxies.
Yeah.
But if the absolute largest structures in the early universe were already silently organizing and shaping their galactic inhabitants just 1.2 billion years after the Big Bang, what massive invisible cosmic structures are currently shaping our own Milky Way galaxy right now?
Ooh, that's a deep question.
Right. We know we are being pulled toward the Great Attractor. We know we are part of the Laniakea supercluster. But what vast unseen gravitational forces are dictating our ultimate evolutionary fate as we fly through the cosmos forces that we simply haven't invented the right mathematical or optical filter to see yet.
It's a humbling reminder that we are constantly swimming in an ocean of gravitational dynamics that we are only just beginning to accurately map.
Keep looking up and keep questioning the empty spaces.